here again. For posterity, I'm going to start recording anyway. Because the first 30 minutes will be for the worksheet, then a 10-minute break, or 5-minute break rather, and then we will continue on. The line integral is next. And it's also called a path integral, right? So instead of integrating over an interval, we're now integrating over some curve. And so you have two types. You have line integral of scalar functions and line integral of vector fields. Pay attention to how they're evaluated. And so for the scalar, this is what we're going to wind up doing. So you have to parameterize your path, and for vector fields, this is what we're going to wind up doing. So again, you need to parameterize your path. Something's wrong. Why? Missing stuff. And the fundamental theorem of line integrals for conservative vector fields. Right, so conservative vector fields are path independent. There we go. That's better. So let's go ahead and evaluate some path integrals. This is a scalar. Oh, they were nice enough to tell us the parameterization of the curve, so we don't have to worry about that. Here. We need R prime. Where is it? What is its magnitude? 625. Magnitude is 5. So you see ds or dr. It's just a length differential. This is going to be the integral from t1 to t2, negative 1 to 2. Take the integrand, evaluate it along the path r. So that means everywhere there's a y, you replace it with negative 3t. Everywhere there's an x, you replace it with 4t. Then it is times your magnitude of the path, of the derivative of the path, dt. That's a simple one. That's you slow, isn't it? U is 16t squared, du is 32t. Negative 15 or 32 e to the 16t squared, evaluated. T goes negative 1 to 2. What's 2 squared? 4? 4 times 16. Negative 1 squared is 1 times 16. What's going on? Go away. Yep. That would be our integral. And of course, we can simplify that. Factor out negative e to the 16. And so that's very straightforward. So again, the hardest part is setting about right. Evaluation is generally pretty simple. Now we're going along the unit circle in counterclockwise direction. First thing you need, parameterization. That should parameterize the unit circle.
Isn't it, since it's the whole unit circle, isn't it just 0 to 0?
Well, that's the name for the parameter. What's the actual parameterization?
Is it cosine to 0?
Technically, it's less than 2 pi. Oh, no, it's the entire. This is close, so yeah, it's going to go back to a starting point. Less than or equal to 2 pi. Return to where we started. What's r prime?
Is negative sine of t cosine of t.
What's its magnitude?
Negative sine squared of t plus cosine squared of t all made squared.
Be careful.
Oh, the sine's not negative.
Negative sign is all being squared.
So,
How's it simplify?
1.
Oh, that's nice. Another way you represent this, because our curve is closed, you'll see that. It's called the circulation. Integrating from 0 to 2 pi, x minus y plus 3 evaluated along the curve.
So is the circulation interval, is that only over?
Circulation is the curve is closed. Times magnitude of r prime dt.
So does that affect how you take the interval?
No.
It's just
It tells you that it's a closed curve.
Okay.
Oh, this is nice.
But I guess there isn't a difference, like it doesn't change anything about integration.
No, it's just specifically telling you that the curve that you're integrating over is closed. What's the period of cosine?
0.
Period of cosine.
Negative 1.
That's range. Period.
Period is distance between the two, so that's just 1. I'm guessing.
How long does it take to start repeating? 2 pi. Look what we're integrating. 0 to 2 pi. We're integrating over one full period of cosine, so it's automatically 0. Oh, but same thing for sine.
So then,
We're integrating over one full period of sine, that's automatically 0.
gotcha.
We're just left with 3 dt from 0 to 2 pi, which is just 6 pi. Oh, for Pete's sake. There's our curve. We want the circulation. Since it's circulation, our starting and ending points are the same.
So
Right? So it's a closed walk.
I guess it doesn't matter where you.
So where we start doesn't matter. So why not just start at the origin?
Yeah.
And notice the directions too.
Would it matter which direction you go in?
It doesn't matter.
I guess those all curves have a direction or
Every path is going to have a direction. Whether they implicitly tell you or explicitly tell you.
is it something you just do?
No, it'll have to be given. So the first one gave you the orientation by telling you that it's -1 to 2 for t.
Right, so it starts at negative and goes up.
That gave you the orientation, told you it's counterclockwise. Here it's giving you the orientation with the arrows. Can't we write this path as 4 individual paths?
Yeah.
So what we're going to do is we're going to take the integral along each of those independent paths and then sum them up. And that would be the total circulation.
What would TS be in this case?
Depends on the path. Right, it's always
So-
r prime of t dt.
Oh, I see. Okay.
R1. Well, that's just the horizontal line from 0 to 1, right? At 0.
Yeah.
Right, so y is 0. Let x be t. And t will go 0 to 1.
And then I guess you just do this for all the sides.
Magnitude of R1 prime, just 1, isn't it? Run out of room, so let's move this up here. R2, notice x is now fixed at 1, right? And y is going to go up. From 0 to 1.
So why did you make x? Why didn't you make x t?
Because x isn't changing, is it?
I see.
X is fixed at 1.
Gotcha. So it's not.
Magnitude is once again 1.
So it's only t is just for the direction you're moving.
R3. Y is fixed at 1, t is changing. Right, but notice how t is changing. It goes from 1 to 0. There's more than one way to represent curves.
Is it in this case?
So this is one way we could do this one. Or, I'm going to do it this way. But that's in the opposite direction. So instead of it being the integral, it'll be negative the integral. Because there's a property, if you flip the direction,
Yeah.
you multiply the integral by -1.
Okay.
So when I go to write out the integral,
'Cause that's-
it'll be along C1 plus along C2 minus C3, because I'm going in the opposite direction.
And you're going the opposite direction.
Right, because this, how I have it written, right? You're going this way,
Yeah.
but we want to go this way. So I'm going to integrate as if I'm going over this way, but then multiply by -1.
Now, couldn't you write it as negative t1 as well?
Negative t wouldn't work.
Why would you make it t1?
Oh, I guess you could do negative t from -1 to 0. Is that what you're doing? That could work. That would work.
Because it's saying y is fixed at 1 and t is moving.
Oh, yeah, that should be 1, not a 0.
And t is moving in the negative.
T goes from 1 to 0. X goes from 1 to 0. So you could do that, negative t from negative 1 to 0. That would satisfy that. So that's what I mean, there's more than one way to parameterize it. I'm going to keep it this way because I want to keep t going the same for all four. I don't have to, but I want to.
Okay.
I want t to go from 0 to 1.
So that's just saying that it's y is at 1,
Mhm.
and then it's going, x is going in the direction of t, which in this case is back towards the origin.
But I parameterize it to be in the opposite direction, and I'll deal with that.
So I guess you could just say for t is less than 1, like you could flip
They can't.
0 and 1.
No, you can't. Because 1's not less than 0.
Oh, that's how you have to make it negative. Oh.
Because you'd be saying that 1 is less than or equal to t, less than or equal to 0, which is not a true statement. 1 is not less than 0. It's greater than.
Okay. I see. I see. Concept I'll have to get used to.
Now x is 0, right, for R4. Y goes from 1 to 0. So again, more than one way to do it, but I think what I'm going to do is parameterize it to go from 0 to 1, and then flip the direction when I go to do the sum.
So the way to write it without flipping the direction would be 0 to negative 1.
Negative 1 to 0, but then that would be a negative t
1 to
instead.
0, yeah.
But then inside would be a negative t. You could also do for t naught equals 1 and t1 equals 0.
Mhm.
You could do that. Right? Your starting point's at 1, your ending point's at 0. But you wouldn't be able to use this kind of notation, inequality notation, because 1 is not less than 0.
There should be more classes where it's just me asking questions. This is great.
So there we go, we have our setup.
Oh man, I forgot that was all just for the setup.
So circulation, and we're at ds over along C would be, and this is where technology is wonderful. Now, minus C3, because I'm going the opposite direction. Then minus the integral along C4 again, because we're going the opposite direction.
So,
Oh, wait, is this going to work? Oh, yeah, well, that's right, okay. Integral from 0 to 1. X was t, y was 0, right? And then ds is just 1 dt. Plus 0 to 1. ds is 1 dt, x is 1, y is t, you get t squared plus 2. Minus integral from 0 to 1. Guess we get 0. Just check for you. That's not going to work.
So you can't split it up. Oh, do you have to do 5 parts?
No. Let's do it something back out to 0. It shouldn't be. I should not get 0 out of this. It should work. I don't know why. I don't know why that's not working. It should. So I'm going to go back to what I was going to do. Just use 1 minus t instead. It doesn't change anything else. T still goes 0 to 1, and magnitude is still 1. And then since this will now be a plus and a plus.
Not even the last 20 minutes.
There you go. It's a big one. So it's a close as it will.
And then that would be this. So I definitely should not be getting 0 out of this.
That's good. I have motion on that.
The antiderivative 1 over t squared plus 1 is the inverse tangent.
So you switched 3 and 4 to be 1 minus 2?
Yeah. T becomes 1 minus 2. Now I'm oriented in the right direction. Right? This is the inverse tangent of t. From 0 to 1, what's the inverse tangent of 1? Pi over 4. And then the inverse tangent of 0 is 0. So that first one just becomes pi over 4. Plus 1 over root 2 times the inverse tangent of t over root 2.
This is what happens.
It's just going to be that, because you're still going to have inverse tangent of 0, which is 0. Now we're going to do minus, because you have to do u sub, right? So negative inverse tangent, negative 1 over root 2 inverse tangent of 1 minus t over root 2.
So we do the same thing as the previous one, so just with 1 minus t instead. Oh, yeah.
It's identical. When you evaluate it. Right, because what's 1 minus 1? 0.
Oh,
So you get
I see.
1 over root 2 inverse tangent of 0 is 0. Minus 1 over root 2 inverse tangent of 1 over root 2 at t equals 0.
So
But remember, that has to be multiplied by minus 1 because you had to do 1 minus t u sub. So that becomes plus 1 over root 2 inverse tangent of 1 over root 2. And same argument for that last one.
yikes. Now we're left with these squared things. That's nice. Should that be pi squared?
It's just sum, it's not multiplication.
Oh, yeah, never mind.
Pi over 2 plus root 2 inverse tangent of 1 over root 2. Total work. Work is just a path integral. Force dot dr. Well, they gave us R. Magnitude of R prime would just be root 2. Oh, I don't need magnitude, sorry. What am I doing? This is a vector field. So we can integrate 0 pi over 2. Now what we have to do is evaluate f along R. Dotted with R prime. dt. Is going to give us dot product negative t sine t plus t cosine t plus cosine t dt. To do that by hand, you would have to do 2 integration by parts from here. And I'm not doing that. So I'm just going to let Wolfram do it for me. Pi over 2 minus 1.
There we go, that's that easy. This can't be done by hand, right?
That can be done by hand, yeah. It's just your first term is going to require integration by parts, your second term requires integration by parts. That cosine t is nice. That's kind of one. Force field is given by that. Find work done in moving a particle once around the circle in the xy plane with its center at the origin and a radius of 3. First thing we need to do is parameterize the path that we're going along. So, circle of radius 3. Center at the origin, 3 cosine t, 3 sine t. And we're in the xy plane, which means z is 0. And it's the entire circle, so t goes from 0 to 2 pi. And that's our prime. Work would then be the integral from 0 to 2 pi. Evaluate f along the path r. That's going to give 6 cosine t minus 3 sine t plus 0. 3 cosine plus 3 sine minus 0 squared. 9 cosine minus 6 sine plus 4 times 0. that has to be dotted. Now with arc prime, which we said -3 sine, 3 cosine, and 0. dt. Do that dot product. Well, that third term's not going to matter, right? Because it's going to get multiplied by 0. -18 cosine sine minus, or not minus, sorry, plus 9 sine squared plus 9 cosine squared. Why am I doing? Oh, let's just do base t. And that looks like what? Plus 9 sine cosine. Nine sine squared plus 9 cosine squared is 9, right? Minus 9 cosine times sine. Factor out the 9. But look what we're left with. Sine times cosine. Is not a half sine of 2t. What's the period of sine of 2t? It's too large.
Oh, sine of t is pi.
It's just pi. We're integrating over 2 full periods. Then it goes out to 0. You're just left with 1 bt from 0 to 2 pi, which is 2 pi, right? Which is 18 pi. So, yeah. Take advantage of that property. You integrate over a multiple of a period of a periodic function, it's 0. Find the work done. Moving a particle from 1, -2, 1 to 3, 1, 4 through the given force field. Let's find its curl. partial y minus partial z. Well, that's just 0, right? Because there's no y's in here, so that's 0. There's no z's in there, that's 0. Partial z minus partial x. That's also 0, right? 3z squared minus 3z squared. Partial x minus partial y. Oh, isn't that 2x minus 2x? The curl is 0. That means F is a conservative force field. That means our line integral is path independent by the fundamental theorem of line integrals. So that means what we're going to do is find a potential for our conservative field. Then it will just be F of, or call it V, be V of P1 minus V of P0. Well, this has three things. Partial of v with respect to x has to be 2xy plus z cubed. Partial of v with respect to y has to be x squared. Partial of v with respect to z has to be 3x z squared. So we have to find a function v that satisfies those three partial differential equations. Pick one. Which one's the easiest? WY. No, you have to find a potential function that makes them all true.
Okay, so you're gonna have to find the
You can, that's one method of doing it.
Okay.
But I find this method to be a lot easier. So I'm first integrating with respect to y. Right? So it's x squared times y plus some function of x and z. Take the partial of a function of x and z only with respect to y, isn't it 0? So a function of x and z is constant in y. Now we have to find that function, that f. I want to take its partial with respect to x. I'm not doing that. Let's see. That's what you get, right? But doesn't that have to equal 2xy plus z cubed? That means that your partial of f with respect to x is z cubed. So what's f? it's just that antiderivative, right? Xz cubed plus some function of z only. Here's where we're at right now. We have to find that g. Now take the partial with respect to z. 3xz squared plus g prime, but that has to equal 3xz squared. Means g prime is 0, right? That means g is just some arbitrary constant. Every potential function will be x squared y plus xz cubed plus some constant. We just need one potential function. So why not choose the function where the constant is 0? And say there's our potential. So we need to evaluate v at the terminal point, which was what? 3, 1, 4? Then subtract v, evaluate at the initial point. 1, negative 2, 1. V at 3, 1, 4. Is what? What's 4 cubed? Times 3.
192.
3 squared times 1.
9.
Add up 2. 192 plus 9. It's 201. V at 1, negative 2, 1. It's 1 squared. Times negative 2. What's 1 times 1 cubed? What's negative 2 plus 1? Work is 202. That's path independence. I'm gonna throw it out back in. That's back in. So let f be conservative, such that f is negative del v for some potential v. Suppose a particle of mass m moves through f from point A to point B. Prove that v of a plus a half mva squared is equal to v of b plus a half mvb squared, where v sub a and v sub b are the magnitudes of the velocities of the particle at a and b respectively. Does that look familiar? Oh, that doesn't look familiar. That's very sad.
Isn't that the acceleration?
That's conservation of energy. A half mv squared is kinetic energy. V is potential energy. So that's saying the total energy at point A is equal to the total energy at point B, which is the conservation of energy. Right? Change in energy is always zero. Through a conservative force field. This is only like the number one law of physics. Energy is conserved. So start with Newton's second law. It says the sum of forces is equal to mass times acceleration. Jack probably doesn't like that law anymore. Newton's second law. Differential equations. Sum of forces is mass times acceleration.
Yeah, that's right.
Notice that if we take the derivative with respect to time of velocity squared, or speed squared rather, that's the same as the derivative of velocity dot itself, right? That'd be v dot a plus a dot b by the product rule. But that's just 2 times v dot a, right? Solving for a, I'm sorry, solving for just v dot a. V dot a is a half of the derivative of v squared with respect to t. Therefore, work is that path integral. Well, that's the integral from point A to point B of f, which is mass times acceleration, dotted with r prime, which is v dt. We can pull mass out. But didn't we say that a dot v is 1/2 d dt of v squared? Factor out the 1/2, you're left with that integral. That antiderivative is just v squared. You get a half mvv squared minus a half mva squared. On the other hand, we're told f is negative del v. That means that work is v of a minus v of b. Right? Because it's negative, you flip the order. But work has to be the same, right? Both of those integrals calculate work, don't they? So that means those two values have to be identical, right? Solve. Yep. When you rearrange terms, you get the desired result. Energy is conserved. only through a conservative force field. The actual law of conservation of energy so take your driving. So you have a potential energy, you have kinetic energy, right? For now, let's just assume that you're driving along a flat road. So we can ignore potential energy. You're going at 60 miles per hour, right? You have a certain kinetic energy with that, right? Now you brake. So you slow down to 25 miles per hour. Your kinetic energy is now lower, right? What happened to that extra energy? Because you've lost kinetic energy. Where did it go? Where did that lost kinetic energy go? Yeah, just like physics 101. And you said you're a Mackie, right? You should know this. Go from 60 to 25 miles per hour. What happened to that lost kinetic energy? Just the ground?
Well, so
Not necessarily. Not just friction. Also braking.
which is also the
What kind of energy is that? No. No. No, kinetic energy is a half mv squared. Kinetic energy is strictly from speed.
which is the friction.
There is a type of energy, it's not kinetic. It's thermal energy.
Oh, yeah, thermals.
Heat. So friction causes heat. So your lost kinetic energy was actually converted into thermal energy, right? Either the brake pads or the rolling friction on the ground. Right? Or drag, that causes heat. We'll make it simple and we'll just say ignore all friction, except for the brakes. Right? So it went into the thermal energy onto the brake pads, right? Was energy conserved?
No,
Because it's not a closed system. Because doesn't heat dissipate? If you come to a complete stop and you let it sit there for a while, the heat dissipates, doesn't it? So you're losing that thermal energy. But that's not a violation of conservation of energy, because your car is not a closed system. Now if you look at the Earth, it's dissipating into the atmosphere. But is the Earth a closed system? Earth radiates heat. It also absorbs heat. It absorbs heat from the sun, it radiates heat. The closed system would be the entire universe. Or, if you're like me, the entire multiverse. So that is an important distinction. Energy is only conserved in a closed system. So if you're looking at a problem that appears you lost energy, you're not violating conservation of energy. It could just be that your system's not closed. so now we're due this worksheet. And while I'm working on that, I'll bring this up real quick. Homework 12 is due August 11th. There will be one more homework after that. And the 5th quiz will be available after today's meeting. So it'll go up at 3:15 today. It'll be due before Wednesday's meeting. And that may or may not be the last quiz. There may be one more quiz after this. I haven't decided yet. We'll see.
Are we having like reviews on class before the final exam as well?
It's not going to be an entire class. It'll be 75 minutes. Last 75 minutes of the last meeting before the exam.
And the exam's on the Monday?
18th. Okay, so finish this worksheet and the rest of the time. Next time we start, we'll start Cynicals.